So I have two regular functions here. One's a polynomial and one's trigonometric. But what if I were to make a mega function that seemed to be the product of these two regular guys? You see, I can differentiate this one very easily with the power rule, and this one from just your basic ideas of trigonometric derivatives. But this one, it's not a trigonometric function, and it's not a polynomial, so what do you do with this? Seems to be just a product of two regular ones that we can easily differentiate. But this one seems difficult. Well, you can do it. All you need to do is just remember what a derivative is. A derivative is a small change in one variable divided by a small change in another variable. And when it comes to functions, a derivative is a small change in the output of the function, m of x, to the small change of the input, x. Derivative is dm over dx. That's basically the derivative, the same as dy over dx. Okay? And how do you find this? You need to find the change in this mess. This product, essentially, is the same as saying d f of x times g of x. Sorry, I'm supposed to put an of x here to make it look consistent. And then divided by dx. This seems pretty complicated, right? How do you find a change in this product? It seems very complicated. You can find a change in this one and this one individually, but this one altogether seems like a lot. But you can actually make that a bit easier if you put it in geometry. The thing about calculus is that, and a lot of math, is that you can simplify everything by making it visual, by making it geometric. Even though it's algebra, you can still represent it with a geometric analogy, okay? So the thing is, we had a product earlier. F of x multiplied by g of x. Where else do we see products? We see it in geometry as areas, right? We can see areas as products of two lengths. So I can represent this as the area of a square or a rectangle, and the lengths are f of x and g of x. Okay? Now, the point is we need to find, now this is basically m of x, right? This was, the original name for this was m of x. Okay? And what we want, the derivative, is a change in x, dx, and a change in m, dm, and we need to find the ratio, which is just the fraction dividing the two of them together, okay? So, the thing is, when x changes, it changes by the small, tiny little nudge we call dx. It becomes from x to x plus dx, okay? And as a result, f of x, any function that can be called f of x, will turn from f of x to f of x plus dx, because it's being substituted with a different number. Instead of being substituted with x itself, it's being substituted by x with a slight nudge being put into the input. Thus the output as a result will also be slightly nudged. And we can rewrite this thing as f of x plus df, which means a slight nudge in the output f. A slight nudge in the input will also cause a slight nudge in the output, so I can rewrite it like this. Okay? Now, let's look at it in terms of area. Let's look at it in terms of this rectangle. If I were to slightly nudge x into x plus dx, f of x will also slightly nudge to become f of x plus this tiny nudge df. Okay? And the length will stretch a little bit, a tiny bit. And g of x will also nudge by a slight amount of dg. Okay? It slightly nudges because x also nudged. The functions also have to nudge too. And as a result, the length getting longer creates this extra area. And we can break this area up into these parts, into, actual right-angled polygons to make it easier. If it was a weird shape, it would be very difficult to find the area of it. But yeah. So because we've broken it up, we can finally find the area of all these individual extra bits. All these bits is the extra result, the extension, the nudge to the entire function itself. This dg is a nudge, is a nudge of g of x. This d of f is a nudge to the function f. But all of this area is a nudge to this function m of x. This entire thing, if I were to just remove the borders separating this entire area. This entire excess area that you've made is dm. This whole area is dm, is the extra bits, okay? And if we just need to break down what these extra bits are, we can break it up into smaller bits. And we can actually know what this area is, and this area and this area. This area has a length of d of f and a length of g of x. So that's df, oh, I can't really write it. df, I'm writing it sideways, times g of x. Yeah, you have to look sideways, sorry. And over here, this area has a length of f of x and d of g. So it's kind of like it's flipped. D of x and d of g. And this one over here is d of g multiplied by d of f. dg, there's not enough space. df, okay, it's going out of the borders. The thing is, when we're finding derivatives, we want the nudge only, the ratio between the nudges, between dm and dx. We don't care about the actual thing. We cared about what was the resultant nudge. So if you want to find dm, this is dm. We don't need to care about m itself. So we can just kill this guy off. I'm sorry, goodbye, you have to die. And then we just have to evaluate what this area is. Well, we know it's f of x multiplied by dg. And it's also, I forgot what the other one was, g of x multiplied by df. And then this little extra bit, dg multiplied by df. I wrote it wrongly. df. Okay, yeah. So, now that we got that out of the way, the thing is, we have to just talk about this little guy first. This little portion, okay? This portion is actually kind of zero. Okay, so the thing about d is not just a difference. It's not a difference. It's a very small difference. You're finding such a small, tiny difference. The ratio gets more and more accurate. The thing about calculus is that you're getting so small. It's smaller than any possible number you can give. You can say it's almost infinitely small, but you know, there's a debate whether that's actually possible to get infinitely small. But yeah, it's kind of like in a graph. If you want to find the gradient of a graph, if you take 2 points, it's going to be inaccurate because it's not, if you treat it like a straight line, it's not very accurate. So you need to get smaller and smaller and smaller, as small as you can, smaller than any possible number. It becomes so small. And the thing is, these d's are really small, are saying they're really small nudges. These are nudges, but so small. That means d of f over d of x, for example, if I had this kind of fraction, this is so small, this is so small, but the ratio is it can be like something that's big, like 2. However, d of f on its own is really tiny. And it multiplying by a smaller one, like d of g, it's so small, it approaches 0. Okay, so if you want to learn about why something that had non-zero area earlier, it looked like it had non-zero area, can be treated as 0, you can look up limits, you can look up how limits work. But this area basically just becomes 0 and we can just get rid of it. So all we have are the 2 rectangles from earlier. This rectangle and this rectangle, remember we cut off those 2 rectangles from the bigger rectangle. So all we have to do, this is our dm. This is dm. Okay? And all you need to find is dm over dx to find the derivative. We divide the whole thing by dx. Okay? Now, what we notice is that because it's a fraction, we can break this up. We can break this up into this divided by dx and this divided by dx. And we can kind of, you know, take this out of the fraction, just make it at the side of the fraction to make it look neater. It doesn't change the value. G of x multiplied by df over dx. And then this one is going to be f of x multiplied by dg over dx, just rearranging. And now, it kind of looks a bit nice, right? You notice that the derivative of a product f of x multiplied by g of x can be represented as just one of the functions first, that's not a derivative, and the derivative of the other function, plus that function and the derivative of the other function. It's like that they're taking turns. It's like they're taking turns of being derivatives. But essentially, that's pretty much it, right? You can simplify dg over dx as like g prime x, and then you can simplify this as f prime df over dx, and then you have, oh, running out of space again. I should really plan before I write. Yep. Yeah, this is the product rule. This essentially tells you how to find the derivative of a product when, you know, the actual function is really complicated, when it's made up of something like x squared over cosine x, or maybe it's like x squared over e of x, you know, like it's this really complicated thing, but you can break it up into multiple factors of a bigger product and treat it as like one of them is an f of x and the other one is a g of x, and you can break it up into all of this. Thus, you have the product rule. It's really elegant, actually. The entire process was like, you know, you have to draw these extra bits, you have to take them out, you have to do this manipulation, but the result is extremely elegant. It's this really nice thing, and all you have to do is get it from geometry to get a good understanding of it. So yeah, that's pretty much the product rule.